Hello. Hello, everyone. Not too many people today. Hopefully more show up. Right. So today we're going to talk about electromagnetic induction. So this is the topic. I think from school physics, this is definitely the hardest topic in school physics. And well, we've not made it easy for you, in all honesty. But let's see. So I'm going to go through some of the actual problems, so you don't, so the assignment isn't too daunting for you. Can I ask how many questions have you managed to do, if any, so far from physics? Hello, Judah. So the question is, how many questions have you managed to do from physics? From the electromagnetic induction assignment? I was 6. Okay. Right. None. And Noah? Been a bit busy. Okay, Judah, is it none because you didn't get to do it, or you couldn't do it? Hello, Jasmine. All right. Okay, so I haven't even looked at it. Okay. So we have example 2 and problem 2, which are pretty much the same thing. I mean, the answer is the same. So let's have a look. It's a bit the questions are a bit I don't know how to describe it. It's just a bit weird because all the planes and directions that you have to consider. So you have to think a lot in 3D. So a lot of 3D thinking here. So a rectangular conducting frame ABCD of size Lx times Lz is moving with a constant speed along the x-axis. The field is directed parallel to the YZ plane. So the magnetic field is in this plane, in the YZ plane. So if we draw, let's say, if we draw the frame in this dimension, Z. If we draw this as Z and down is Y, yeah, so Y is down. So we're looking at it from here. We see the frame and A is here, B is here. So C is behind B and D is behind A. So we're looking at it from here, okay? Then the magnetic field is going, well, let's say that way. Magnetic field B. All right. Is that making sense? Does the diagram make sense? Yeah, so if you're looking at it from the back, from this side, look from here. Tell me something. Noah, Judah, Jasmine, does it make sense? Kieran. Right. Okay, so that's this is the example 2. In problem 2, this is example 2. Example 2. In problem 2, the difference is that the magnetic field is in the other plane. So let's say if we draw X and Y direction. If we draw the X direction and the Y direction, then this would be A and D. So we're looking at it from here. Look from here. And the magnetic field is this way. Okay. 2. Okay, so in example 2, we have L Oh yeah. Okay. In example 2, we have 2 EMFs induced. So EMF in AB. And well, let's consider all of them. EMF AB, EMF BC. So we're using the motional EMF. No EMF. And we know that. Does everyone understand motional EMF, or would you like me to say a few words about the motional EMF? Would you like me to explain motional EMF, or you're happy and you understand what it is? Okay. Yes, happy to explain. So let's say we have a piece of wire moving through a magnetic field. This is the magnetic field, and this is a piece of wire. And piece of wire, and it's moving with velocity v. And the piece of wire is of length, let's call it length L. Right. Now, wires contain free electrons. So let's consider a free electron inside the wire. So there's an electron inside here. The electron is a charged particle moving through a magnetic field. Therefore, the electron experiences a force, and this force can be found using the left-hand rule. The field current force. So there will be a downwards force. If you don't know the left-hand rule, please make sure you know. There are plenty of videos explaining it. There's a force, the magnetic force on the electron. So it's a charged particle moving through an electric field, and it's Fm. So Fm is equal to Q V B multiplied by well, we don't really need to worry too much about this, but yeah, sine theta. Well, sine is the angle between the magnetic field and the velocity. Okay, QVB sine theta. Right, but what happens then, because the electrons are pushed down, the bottom part of the wire becomes negatively charged because the electrons are pushed down. And the top becomes positively charged because electrons have left Now, because there's a positive charge here and a negative charge here, there's an electric field inside the wire. And if there's an electric field inside the wire, the electron, the free electron inside, will now be attracted upwards towards the positive end, and this would be an electric force. And because ultimately the electrons, there are nowhere for the electrons to go constantly, they will, these two forces will balance themselves out. I mean, it can't be otherwise. Otherwise, you'll have a current inside a disconnected rod, which is not, yeah, which doesn't make sense. The electric force, as we know from the electrostatic assignment, is the electric field times the charge, and the electric field, if it's a uniform electric field, it's the voltage across the ends, the potential difference, divided by the length of the rod. Yes, we know that the electric field is the voltage divided by d, by the distance, so times q. And these have to be equal because the electron is not moving. So q v b sine theta equals v, that's the voltage, and this is the velocity, divided by L times Q. Q cancels, and we have the voltage, the motional EMF, is equal to L V B sine theta. So if a wire moves across a magnetic field, there will be an motional EMF across its ends. Does that make sense now, Judah? Okay, and it's just EMF. So it's EMF divided by L Q, of course. All right. So there will be an EMF induced in each of the rods. Well, two of them actually. We'll see AB, BC. EMF induced in CD, and EMF induced in DA. In EMF induced in AB is going to be LZ, the length of the rod, times the velocity, times the LVB. So then we have the magnetic field at point A, because the magnetic field is changing. B, and then we need sine of the angle. But now we have theta. Theta is this angle. And we need the angle between the wire and the magnetic field. So we need this angle. And this is pi over 2 minus theta. So that's pi over 2 minus theta. Pi over 2 minus theta. But sine pi over 2 minus theta is, somebody help me? Shout out or...
Cos theta.
Yes, it's cos theta, and VBA cos theta. Very good. Now EBC, in BC, the angle between the velocity and the wire itself is 0. So it's going to be LX times V times BA times sine 0. Oops, sine 0, which is 0. And similar for DA, it's going to be LX times V times BD times sine 0. sine 0, so that's 0. And the CD is LZ, that's the length, the longer side of the rod, times V, times B at point D. So these are different, times sine, well, cos theta, similarly, cos theta. Right, so let's have a look. What's going on with the field? You can see that the field here, the lines are closer, and as you go further, the lines get further apart. What does that tell you about the field? Yes, Adam, it gets weaker. Jasmine, no, the theta, it's either the angle between, if you're talking about the Lorentz force, which in this case it is the angle between the velocity and the magnetic field. When you're talking about flux, it's the angle between the normal to the loop and the magnetic field. Okay, so these are two different scenarios. Right. Okay. So it takes weaker. Well, it's changes. Ultimately, it's changes. Right. Therefore, you can see that the wire AB is in a stronger magnetic field than CD. That means that EMF induced in AB, well, the modulus of the EMF produced in AB is greater than the EMF produced in CD, just because the field is stronger. Therefore, there will be more EMF. And then what we have is the total EMF. So total EMF is the EMF in, well, let's say CD minus EMF in AB, because the EMFs are opposite to one another. One EMF is pushing the electrons clockwise, and the other one is pushing anti-clockwise. You can work out which one using the left-hand rule. So left-hand rule, the field is going away from me. The current is, or positive charges are moving to the right, and the force on a positive charge would be upwards. So you would have an EMF induced. This is plus and this is minus, plus and minus. So this is EMF AB, and this is EMF CD. So ultimately, you'll have a current you will have a clockwise current through the loop. Right, so EMF is that, so that's going to be L EMF is ECD minus EAB. So that's LZ V cos theta. And you can see that the only difference is the B. Yes, so this is L, this is what they have in common. If we multiply by B D minus B A. Right. And if we divide this, so that's the change. So that's well, that's the change in B times LZ V cos theta. And we divide this by delta X by the length, by delta X, which is AD. It's the distance. So how much does B change over this distance? So this is delta X, and multiply this by delta X. All right. So we have delta B, change in B, over delta X. And for small changes, we can write dB dx LZ V cos theta and delta X. What is delta X? What is delta X in terms of the initial values that we have? See how well you're following. Lx, very good. Yes, delta X is Lx, so therefore we have dB dx LZ Lx V cos theta. And this is the answer. This is the EMF. Yeah, this is the induced EMF. Oh, where we need we need the current, right? Yeah, so we need the current. So current is EMF divided by R. So that's dB dx Lx Lz V cos theta divided by R. Right. Now, problem 2 is the same thing, but now we have a different angle. Well, not a different angle, a different plane at which the field is coming from. But here we have EMF. Right, so we have the movement in this direction, and the field going how I started the problem. Yeah, so the example 2. So what I did is I have drawn out the diagram for example 2. So this is the z-axis and this is the y-axis. So here they are. The axes are here, just to make sense of what is what. So this is a three-dimensional situation. So we need, if we're looking from here, that's example 2. Example 2. So this is just a diagram of the same thing from the point of view of example 2, and this is for problem 2. Problem 2. And so for problem 2, we have, well, it's the same. The answer is going to be the same. It's just the, so what are we talking about? The velocity. Okay, so we have the velocity going that way. We have the velocity going that way. And we have the magnetic field going that way. the magnetic field. This is the velocity. And we have the Lorentz force. We have the force is equal to, you need the angle between this, and this angle is again pi over 2 minus theta. So the force, the Lorentz force, is QVB sine pi over 2 minus theta. And it's going to be QVB cos theta again. And the EMF induced is going to be QVB not QVB, QLVB. LVB cos theta. So, and the look, problem 2 has all we need to do is just show the equivalence between problem 2 and example 2. Okay, so EMF in this case you know what, I'll do a different approach for problem 2. Sorry, do a different approach for problem 2. The flux going at problem 2 is B times times the area multiplied by the cosine theta. Okay. So this is the normal to the loop. This is the normal to the loop. Normal to the loop. This is and the angle is theta. All right. Don't look at the fact that it's pi minus theta, because you might as well just direct n downwards. Okay. Right. So the flux going through the loop is BA cos theta, and we know that the yes. So why does the flux change? Well, the flux changes because B changes. So we can say that the EMF induced is minus the change of flux divided by change of time. So all we need is we need to differentiate that. But these are constants. So that's going to be minus A cos theta multiplied by dB dt. Okay. So we're kind of using the chain rule here, if you want to say. The EMF is the derivative of phi with respect to time. It's minus A cos theta dB dt, and that's going to be we use the chain rule again, minus A cos theta multiplied by dB dx dt. We know that dx dt is the velocity and dB dx is given. So it's going to be minus A cos theta dB dx multiplied by the velocity. And we remember that A, the area, is Lx times Lz. multiplied by cos theta, multiplied by V, multiplied by dB dx. And finally, the current is the EMF divided by the resistance. And that's that's the same answer. Well, dB dx. The only difference is the minus, which doesn't really mean anything because what does the minus mean? Which way is positive? Like you have a loop with wire, cos theta. How do you tell which way is plus and which way is minus? You don't really have a way of saying. So the answer is the same. So I've done problem 2 for you. So you can use this solution in your assignment. So I'll just circle that this is problem 2. Problem 2. Okay, the other problems are going to be easier. So it's very like a needle in a haystack with this problem. Here, the conductor is sliding on 2 metal rails as shown in the diagram. The resistance of the light gray frame is negligible. The resistance of the dark gray bar is R. Consider the 3 cases. The field is perpendicular to the frame. The field is parallel to the XY plane. And the field is parallel to the YZ plane. Show that in all cases, the current circulating in the loop equals BLV cos theta over R. Well, the easiest way to do this is just say, look, we have the flux. We know the EMF induced is the change of flux divided by change of time. There's a minus here, but once again, like what is positive in this case? It's not really a thing. So the minus doesn't mean anything here. I mean, it certainly does have a meaning, but it's doesn't change your answer in any way. Right, so you need the flux, and the flux is B. Flux is B multiplied by the area multiplied by cosine theta. Well, in this case, it's perpendicular, so theta is 90 degrees. Right. Now, how do we differentiate that? Well, B is constant. Cosine is constant. A is not constant. So that's going to be minus B cos theta multiplied by dA dt. Does that make sense to everyone? Because you can, when you differentiate, you can take the constants out. So that does make sense because theta dA dt. And what's dA dt? Well, let's find what A is. Area is length multiplied by x, where x is this distance, Lx. So dA dt is cos theta is L multiplied by dx dt, which is LV, which is minus B LV cos theta. And the current, so in A, the current is EMF divided by R multiplied by minus equals minus BLV cos theta divided by R. This is this is 90 degrees, so therefore it's just minus BLV. LV divided by R. In B, it's the same thing. and then C is the same thing. But this is doing it through the point of view of flux. Okay, so what I would like you to do in this case is do it from the point of view of the motional EMF. Motional EMF. So you have a length of wire which is moving through a magnetic field with velocity v, and the motional EMF motional is LVB sine pi over 2 minus theta, which is cos theta again. Right. And when it's parallel to the XY plane, this way, yeah, so just looking at it from different perspectives. Now, ultimately, what you need to understand, actually, it does not matter how the flux changes. Does not matter how the flux changes. It could be the, doesn't matter how the flux changes, the motional EMF, the EMF induced is equals minus d by dt. This is the gist of Faraday's law. Faraday's law. Okay, so problem 3. Problem 4. So Gauss law for electricity and magnetism. Okay, so we've done Gauss's law in the electrostatics assignment, and it's just worth going through. Right. Second. Yeah. So for electricity, the Gauss's law. So Gauss's law, if you have a closed surface, and you have a charge inside Q, then the total flux going through that surface going through that surface is Q divided by epsilon 0. This is the Gauss's law. So the flux of the electric flux going through a closed surface is proportional Now to the charge enclosed in that surface. Does that make sense to everyone? Do I need to explain more? Yeah, and the flux for a small area, let's say you take a small area, dA, the small flux going through that area is the electric field times dA. Does that make sense? Sure? No problems here? Adam, it makes sense to Adam. What about Kieran, Noah, Jasmine, Matty, Hannah? Now, with magnetic fields, if you have a closed surface, the magnetic fields are circular. So we can either have a magnetic field going like this, the magnetic field lines are closed loops as well. So because the magnetic field lines are closed loops, we don't have a point of origin. Like magnetic lines don't have a starting point. They don't emerge from anywhere, even though sometimes magnets are drawn with the field emerging from the North Pole. It's not the case because the magnetic field goes out of the North Pole, around the magnet, into the South Pole, through the magnet and back out. So magnetic lines are always circular. So if you have a closed surface and the magnetic field passing through the closed surface, you can always be 100% sure that the number of lines entering this surface is equal to the number of lines exiting it. So for example, you can have a loop inside. You can have a loop like this. The number of lines entering is, so the flux going in is equal to the flux going out. So the total flux is 0. And this is Gauss's law for magnetism. It's super easy. Gauss law for magnetism. This is basically saying that magnetic charges do not exist, magnetic monopoles. They're magnetic charges. Monopoles do not exist. So you can't have a magnet you can't have just a north magnet. Yeah, you can't have just a south magnet. So yeah. Now, the existence of magnetic monopoles has been argued for quite a long time, and potentially, but they might exist. And if they do exist, well, we'll have to rewrite the laws of electrodynamics. But so far, these haven't been discovered. Okay. I'll give you some more hints on some of the problems, and then we'll go to some tough ones. All right. Okay. So a galvanometer with a resistance 100 ohms is connects two rails of a railroad separated by 1.4 meters. So we have a railroad. These are two rails. We're looking from the top. And there's a galvanometer galvanometer is basically a resistor. Oh, sorry, is an ammeter or a volt. It's somewhere in between a voltmeter and an ammeter. This is a galvanometer. So these are 1.4 meters apart. A train is approaching with speed, so a train. And as you know, trains have these wheelbases, which look like this. The wheels of a train. Does everyone have an understanding how train wheels look like? Like this. Okay, they always look like this. There's a tough bar, and yeah. Actually, there's an amazing thing. The train wheel is an amazing thing. The question is, how does it stay? How does it stay on track? Does anyone know? How does the train not fall off the track? Are you talking about these rims, Hannah? So it's not. It's not. So just Google Richard Feynman train wheels, and there's a fantastic explanation. I don't want to go too deep into this. So the rims are just a safety feature. They have nothing to do with the train staying on track, except in really bad circumstances. The actual reason is that the shape, like this wheel is slanted. This wheel is like, if you look at the cross section, it looked like this. And it stays on the track because of that slant. I don't want to deny you the fun of figuring it out. So do try to figure it out, or just Google Richard Feynman. Train wheels. You should find it. And there's a fantastic explanation of why this happens. So anyways, and they're made of metal, so you can imagine that current can flow through. So you have a circuit here. You have two rails, the galvanometer and the train, and that's a closed circuit. So current can flow. The train is approaching at 60 kilometers an hour. So the velocity is 60 kilometers an hour. And what current will the galvanometer show? The vertical component of the Earth's field. So the vertical component, so that you have a magnetic field of the Earth. And in the northern hemisphere, it's down. So crosses. In the southern hemisphere, it's going to be upwards. But that still doesn't change anything. And the solution is the same as before. Yeah, so solution as problem 3. See problem 3. Problem 3. Okay. Now, problem 5, I love this one. Now, this is a really tough one. A round loop of wire is placed into a uniform magnetic field. So this is the initial situation. Uniform magnetic field. There's the magnetic field going through the loop. When the magnetic field is switched on, so initially there was no magnetic field, it was switched on, and there's a current flowing. So if the magnetic field is going away from us, when it's switched on, which way will the current flow? Clockwise or anti-clockwise? Lenz's law. Field. The field is increasing. Very good, Adam. Yes, it is anti-clockwise. Can somebody explain why? Use your mic. Now these are A-level questions. Yes, to the right thumb rule, that is correct. Can you elaborate on this? Now, this is an A-level question, right? Problem 5 is not, but this is an A-level question. Field is increasing, which way is current? No? You do use the right thumb rule. Okay. Who knows why? Apart from Adam, who knows why the current is going to be anti-clockwise? Okay, vote. 1, I know, 0, I don't know. And it's fine that not to know. The right-hand thumb rule, yes, the right-hand thumb rule, that is correct, but how do you use it? I'd like an explanation how it is done. Because if you use the right thumb rule, okay, right. Okay, so we have a loop of wire which is inside a magnetic field. So we have a loop of wire. Yeah, Jasmine, but if you do this, the current is going to be the opposite direction, according to that. Thumb for magnetic field and thumb for current, yes. Now, this is the Lenz's law. Lenz's law. Lenz's law. The current, the induced current, the current will be induced in such a direction direction as to oppose the change that induced the current in the first place. The current will be induced in such a direction as to oppose the change that induced the current in the first place. So we have a loop of wire. Field through the loop is increasing. Field increasing. The loop doesn't like this. Like this. It produces its own field in the opposite direction. Opposite direction. Out of the page. Yes, that is very cool, actually. Field increasing into the page. Loop doesn't like this. It produces its own field in the opposite direction. Therefore, the current is anticlockwise. Current is anticlockwise. Yes, the right-hand rule. So you have the thumb shows the direction of the field. So the field is out of the page, and the curl shows the direction of the field. So the current, which is anticlockwise. Okay. Who understands it now? Who still doesn't understand it? 1 or 0, please. Hannah, what about you? Good. Right. So when the field is increasing, the current will be in anticlockwise. Does the increasing field just induce the current because of Faraday's law, change of flux over time? Yes, exactly. That's exactly what it does. Right. Okay, so that's the loop. So there will be a current, and there will be a charge passing through the loop. Okay. And here we have so the current is EMF divided by the resistance, which is equal to change in flux over change in time. Now the direction doesn't really matter here. Change in flux over change in time multiplied by 1 over R. And we know that we multiply by delta T. So current times delta T is equal to minus delta phi divided by R. And that's the charge. So charge is minus delta phi divided by R. That's the charge that flows through the loop. Which is equal to That's a bad idea because R is the radius of the loop. So small r. Small r. And that's equal to minus phi. So change of phi is, so it's b times area, which is pi r squared over r. Okay, so that's the charge. Now, that's the charge that flows initially. That's the initial charge, charge that flows. Now, the answer to this question depends on how you fold it. There are three ways. There are three ways to fold it. So first, you can fold the wire like this. So A, and the wire is folded like this. So you will have so basically what happens here, fold it like this, fold like this, this. So area goes from A to area goes from pi r squared to, that's two circles. One is r over 4, and the other one has to be 3r over 4 to pi r squared over 16 plus 9, so pi 9 r squared over 16, which is 10/16 pi r squared. So the area goes down from pi r to 10/16 pi r squared. So the charge that flows is going to be B multiplied by, well, it's going to be change of flux divided by the resistance of the curve, which is going to be, this is Q, let's call this Q0, delta phi over R, so that's going to be B multiplied by 10/16 pi R squared over R, and that's equal to 10/16 Q0. Right. Oh, 10/16 is 5/8. 5/8 Q0. So yeah. So all you need to remember, you need to remember that the charge that flows is the change in flux, and the flux changes because the area changes. Yeah, we're reducing the size of the loop, therefore the flux will change, so there won't be charge passing through. The second type, B, fold like this, fold number 2, number 1, fold number 1, fold number 2, is when you have the small loop and like this in the figure of 8. Okay. And so there's going to be a different solution. And there's a fold number 3. Fold 3 is when you go like this. This is a different case. So in the first case, you flip the top one, and in the second case, you flip the bottom one. And that's a difference. There's the decreasing field. Okay. Flip top, and here you flip bottom. Okay. Right. So work it out. Work it out. 3 marks is. We'll probably award 3 marks for any of the 3 complete solutions. Oh, 2 marks for a complete solution and 1 mark for acknowledging that there are 3 solutions. Right. Okay. Now the next one. 2 metal rails separated by a distance L are placed in a uniform magnetic field that is perpendicular to the plane of the rails. A conductor of mass M can slide up and down without friction while remaining horizontal and connected to the rails. Determine the steady speed of this conductor in the if the upper end of the rails are connected through a resistor R. What types of energy does the work done by gravity transferred into? Transferred, oh, sorry for my English here. Anyways, as the bar slides down under gravity, so the gravitational force mg, the flux is increasing. So the flux is equal to the B times area. Yeah, flux is B times area. So the change of flux, d phi dt, is equal to minus. I always put minus just for the sake of it, but in most cases it doesn't make any difference. So that's equal to b multiplied by L multiplied by x, where x is the distance. So d phi is going to be minus BL dx dt, which is minus BLV. That's the speed. And the current is going to be EMF divided by the resistance R. So that's going to be minus BLV divided by R. On the other hand, there won't be a current flowing. So there's a magnetic flux. There's a magnetic flux going out of the page. There's a magnetic field going out of the page, and the loop is increasing. This is important. Magnetic field out of page, field, sorry, flux increasing. The loop doesn't like it. A current will be induced. Which direction? Clockwise or anti-clockwise? Clockwise, yes. Induced clockwise. So the current will flow in this direction. It has to be flowing in this direction because, yeah. So there's a current flowing through the wire, and now we can use the left-hand rule. So the field is going that way, the current is going that way, so there's an upwards force. There's an upwards motor effect force. So it's a wire inside of magnetic field. So Fm is the motor effect. So F is equal to BIL. BIL. Okay. Now, because these two forces are equal, because it's moving at constant speed, that means BIL is equal to mg. Okay, and current we already know that is BLV over R. So it's going to be B times L times BLV over R is equal to mg. We drop the minus because so that's L squared, it's L and L. It's B squared L squared. So V is equal to RmG divided by B squared L squared. I kind of have doubts about this. Like BLV. No, it looks right. Looks right. The answer just looks a bit horrible with squares. Okay, so that's problem 6. I'll delete this so at least you have something to do. It's too easy. So Fm is equal to Fg. Fg. Okay. Problem 6. All right. I also wanted to look at okay, this one, problem 10. Now, problem 10 is a nasty one, I'd say, but it's not that difficult. You just need to use the example 6. Example 6. But before we do this, I kind of want to talk to you about inductors. Like, what do inductors do? Well, let's say you have an inductor. What do inductors do? What are inductors? Do inductors do? Okay, so let's say you have a battery, switch, an inductor, and an induction coil. No, okay, let's put it this way. Let's say the switch is closed at T0. T0, and this is the current versus time. This is the resistance, and this is the EMF. How will the graph look like? How will the graph look like for this? The switch is closed at T0. Closed at T0. Does it gradually increase? Exponentially. No, actually, it changes like this. So it's 0. It's 0 until t0, and then it becomes like this. So that's the EMF over R. That's very simple. This is what happens when you switch on a resistor. Yeah. Now, if you have the same thing but with an inductor, if you have the same circuit, you have a resistor and an inductor, and you have a switch. The inductor of induction L and no resistance. Yeah, so you have, it's a coil with very low resistance, so R equals 0. And there will be a different picture. The current will start increasing. Just a second. EMF. Yeah, it would start increasing like this. And it will end up being the same, EMF over R. So the inductor smoothens out. So how does it do that? The inductor introduces some inertia to the system. So inductor uses the Lenz's law. As the current through the inductor increases, the magnetic field inside the magnetic field of the solenoid, magnetic field of the inductor, which is a solenoid, increases. And what does it do? If the magnetic field is increasing, the flux is increases. Somebody tell me what's the next phrase which I use? Flux increases. Loop doesn't like that. It induces a current in the opposite direction, thus reducing the overall current. Yes. So as soon as you flip the switch, the current starts increasing, but the coil doesn't like that. It says no, wait. I don't like change. I really don't like change, and it's pushing back, reducing the current. And next topic would be the actual differential equation of this. Okay, so we have the current is increasing like that. So it's not Yeah. Okay. Anyways, if you look at the example, the flux through the coil is the sum of the flux, the external flux, and the flux due to the current in it. So you have the flux due to the current inside the coil. So the EMF, the total EMF, is the total change of flux, the EMF inside the coil. And these have two components: the change of the external flux plus the change of the flux produced by the coil itself. So we're going to apply this. So what's going to happen? So when a switch is closed for a while, this is a simple circuit. When the switch is closed for a while, you have current flowing like this. You have the total current. So the current here is okay. Jasmine is asking, I don't quite understand why, because the current isn't being induced in the first place. The magnetic field is induced. How does the magnetic field induce more current? So we have no current whatsoever. We have no current and there's no magnetic field inside the coil. As soon as you flip the switch, the current starts to increase. As the current increases, the magnetic field through the coil increases as well, because the coil produces its own magnetic field. And then the coil itself doesn't like that change. It's producing its own field, but it doesn't like it. It says, no, I would like to reduce that, please. And it induces its own EMF. So this is the kind of external EMF. So this is the EMF produced by the battery. The coil starts producing its own EMF in the opposite direction. So the coil produces EMF where this is plus and this is minus. Here, plus and minus, and this produces EMF in the opposite direction, and therefore reducing the overall current. It's better to say the EMF is induced in the coil rather than current is induced in the coil. Does that make sense? So the current is lower than it would be if it was just a resistor with no induction. So the induction kind of staggers the process. Also, another thing to consider: the inductor stores energy, just like a capacitor. Just like a capacitor. The inductor stores energy. Right. The energy stored in a capacitor, energy, is equal to 1/2 L I squared. That's the formula for the energy stored in a capacitor. L is the inductance, and I is the current flowing through the inductor. Right. So at first, as some of the battery supplies energy. Battery supplies energy, and it is split between inductor and a resistor. When the current grows to a maximum, the inductor stops draining energy, but the resistor continues to drain energy. Yes, the resistor continues to produce heat. Okay. Okay. So what's going on here? So the switch has been closed for a while, and there's a current flowing. So this is just a normal circuit. You could say that this is a resistor, and that's it. So the current flowing here, I, is EMF divided by R. This is also EMF divided by R, and this is 2 EMF divided by R. Doesn't really matter, just like this. Okay, so when the switch is open, so this part is disconnected. Once the switch is open, the switch is open, we have an inductor and a lamp. Right. And just as before, we write that EMF produced in the inductor is the change in flux divided by time, which is equal to L di divided by dt. This is given to you in the formula booklet. Right. EMF like this, L di dt. And on the other hand, EMF is equal to they are in parallel, so they have the same voltage, and that's equal to IR, current times R. Now, putting the minus here doesn't really make sense if you think about it. So, not the formula booklet, sorry, in the assignment. It's given to you in the assignment. Assignment booklet, that's what I meant. Right, and so we write this and we multiply this by dt. So L di equal IR dt. And we integrate this from current goes from I to 0, from initial current to 0, and time goes from 0 to infinity. Right. So this is going to be L just a second. Yeah, okay. So it's I think I made a mistake here. F divided by to R. So when when this happens, okay, we need to step back a little. So there's a current flowing through this inductor, and inductors don't like change. So the moment you switch it off, the current through the lamp changes direction. The current through the lamp becomes the opposite, because initially the current through the lamp is going downwards, but the inductor will take over because the inductor produces EMF, and the current will go this way. So the current through the lamp will go in the opposite direction. And this won't go for some time until so there will be some charge passing through the lamp. And here, if we integrate this, is going to be L. Oh, that's where the minus went. Okay, that makes sense. So you do need a minus here. So this minus, so it's going to be minus minus. So IL I0 equals, now I dt, as you can see, I dt is the charge. The integral of I dt is the total charge. The integral of I dt is Q. So that's equal to QR. The only thing is, so now we have a resistance. We have double the resistance of the circuit. So this will be EMF is RQI. So it's 2R. It's 2IR here. 2IR. So that's 2IR. That's 2QR. So yes, and the charge is equal to L I0 divided by 2R. And I0, we know that I0 is EMF divided by R. So it's L EMF divided by 2R squared. And that's the answer. Did I just do the whole question? Yes, I did. Sorry. Okay. Hope that helps. Hope that helps. Hope you have a better understanding of inductors and the Faraday's law and the Lenz's law, most importantly. And yeah. Well, I'll see you. Oh, I might not be here next week. I'm moving, but there won't be a webinar anyways. Okay. See you everyone.